So let us continue with looking at inverse DTFT formula and some of the consequences. So we are looking at some sequence and transform pairs which were not part of our attention, or other things are not possible when you consider the Z transform of such sequence. And one of the sequence was this. And we can also rewrite this as 2 pi delta tilde of omega, where if you recall, we mentioned that the tilde notation is used for denoting things that are periodic. So the DC sequence has an impulse train as the transform. And note that x of n equals 1 for all n does not possess Z transform. And this is analogous to x of t equal to 1 having continuous time Fourier transform 2 pi delta cap omega, and x of t equal to 1 for all t does not possess bilateral Laplace. And moment you have this, immediately you can get the transform of e to the j omega naught n using the modulation property, and this of course is 2 pi delta omega minus omega naught. And again, if you use the delta notation, you have to specify the range, and this is the same as 2 pi delta tilde omega minus omega naught. And we had already seen the result here when we are looking at time shift, and when we were pointing out how the phase shift introduced in the transform domain for the DTFT can be viewed as a rotation in the complex plane. In that context, we had seen this, and now we are actually formally deriving this relationship. This of course is pi times delta omega minus omega naught plus delta omega plus omega naught. All you need to do is you need to take e to the j omega naught n, the transform of that, and when you express cos omega naught as e to the j plus e to the minus j by 2, you'll get the final answer. And similarly, sin omega naught n is pi by j times delta omega minus omega naught minus delta omega plus omega naught. So, yes, question. Yes, so that is understood, because when we were looking at e to the j omega naught n, when we first introduced that, we noticed that if you replace omega naught by omega naught plus 2 pi, you don't change anything. Therefore, you will get the same signal if you view omega naught as omega naught mod 2 pi, right? So in this context, just to make sure I understand where this is coming from, no additional thing need be said here, because even if omega naught were not in the range 0 to 2 pi, if it were outside this range, is the question then won't this impulse be located at that particular frequency? Is that the question? That is, was the one that was making you ask? Then immediately the periodicity will generate a complete train. Moment you realize that it has to be periodic, even if omega naught were not between 0 to 2 pi, if it were some other value, the impulse would indeed be located at that particular value, but then periodicity will again make an impulse show up in the range minus pi to pi, which will be equivalent to replacing omega naught, which is outside 0 to 2 pi, in the range 0 to 2 pi. If we take mod, everything will be consistent. Okay. And now, similar to what was done in the continuous time Fourier transform case, we'll look at this particular sequence, the sine function, the Signum function, and we'll show that this transform is 2 by 1 minus e power minus j omega. And the way this sine function is defined is like this. So it is 1 for n greater than or equal to 0 and minus 1 for n less than 0. So this is n, so this is 1 and this is minus 1. And the reason I am mentioning this is in the continuous time case, you had SGN of t, and its definition was like this. So this is t, this is SGN of t. And since this is an odd function, you can go ahead and define the value at t equal to 0 to be 0. So this is 1 for t greater than 0 and minus 1 for t less than 0. Whereas the way this is defined here for the discrete time case, at n equal to 0 it is defined as 1. You can also define another variant of this. You can define the sine function to be like this. In the discrete time case, and then you can at the origin define the sine function to have the value 0. So this now seems to be the counterpart for SGN as defined here. The continuous time Signum function, that odd symmetric function, that counterpart can be thought of to be this. But what we are going to do now is we are going to derive the transform of this. And once you derive the transform of this, it's easy to derive the transform of this with very simple manipulations. So now what we are going to do is we are going to do exactly what was done when you derived the continuous time Fourier transform of SGN of t. What did you do here? In SGN of t, what did you do? No, it could not have been u of t plus u of t. No. No. What was it? That was the sequence of steps that were used to derive the CTFT of SGN of t. Well, each one of you is saying a different answer, right? I mean, this is something that you must have seen. If you had seen this, then all of you must be saying the same thing or roughly the same thing, whereas you're giving completely different approaches here. So what was done was you have replaced this by this, and this of course is e power minus at u of t, where a is between 0 and 1, and this was minus e power minus at u of minus t, and then you let limit as a tending to 0, so that e power minus at u of t as a tended to 0 would tend to u of t. All right. So what we are going to do discrete time case is exactly that. So we are going to I am going to draw the continuous time envelope, but what I really mean is the discrete time sequence whose envelope is this. So I'm going to do something like this, and then I'm going to take the limit of a parameter going to 1. All right. So you'll see that it all makes this once I write down the equation. So I will write x1 of n as a to the n u of n, where a is between 0 and 1. So this would correspond to the exponential for n greater than or equal to 0 part. Then for the negative indices, I am going to replace this with minus a to the minus n u of minus n minus 1. So this is indeed this sequence whose envelope I have drawn here. And then if I now let a tend to 1, then I will get the SGN sequence as defined in this case. So this of course is a to the n u of n minus a to the minus 1 power n u of minus n minus 1. And now we know the transform. So this is 1 by 1 minus a e to the minus j omega plus 1 by 1 minus a inverse e to the minus j omega. And now we will take limit as a tending to 1. So if you let a tend to 1 in each of these terms, you will get this will tend to 1 by 1 minus e to the minus j omega. This will tend to again exactly the same term, 1 by 1 minus e to the minus j omega. Therefore, in the limit 1 by 1 minus a e to the minus j omega plus 1 by 1 minus a inverse e to the minus j omega, this of course will be 2 by 1 minus e to the minus j omega. And hence SGN as defined like this so this is 1, this is minus 1, this is n. Therefore, this sequence has transformed 2 by 1 minus e to the minus j omega. And if you recall SGN of t, its transform is continuous time Fourier transform of the sine function as shown here. Its CTFT is yes. You can almost guess, right, based on this picture. Very good. It is 2 by j omega. This after all is 1 by s plus a, and this also you can it will be 1 by s minus a, right, and then you are going to take limit as a tending to 0. Therefore, it will be 2 by rather rather than S, you would have worked this out in terms of the Fourier transform, will be 1 by j omega plus A, and then you are going to let A going to 0. So, you will get two terms that each of them will be tending to 1 over j omega, therefore, you will get 2 by j omega. Should remind you of this, and the reason why you did Sgn of t was because the very next function that you wanted to obtain the transform of was u of t, right. So, we will follow exactly the same pattern here. So, now we will look at q of n. So, this is nothing but 1 plus Sgn of n. If you did 1 plus Sg of n, this will be 2 times u of n. Therefore, you really want half of this. Therefore, this now becomes 1 by 2, and the transform of 1 is 2 pi delta omega, plus this of course is 2 by 1 minus e to the minus j omega, and because delta of omega is sitting here, we have to qualify this by specifying the range, or if we had replaced delta of omega by delta tilde, we need not have written this. So, this immediately becomes pi delta of omega plus 1 by 1 minus e to the minus j omega. And if you recall, the continuous time Fourier transform of u of t was plus 1 by j omega. You can almost immediately see this because you can write u of t as half times 1 plus Sgn of t. So, now you see the similarity between that and this. So, now you have the Fourier transform of u of n. Note that you could not have obtained the Fourier transform of u of n from the Z transform of u of n because no, you cannot replace Z by e to the j omega because the ROC does not contain the unit circle. So, exactly the same thing that was happening here in the continuous time case, 1 by S, and the region of convergence is real S greater than 0. Therefore, you could not take the Laplace transform of 1 over S and replace S by j omega because the region of convergence does not contain the j omega axis. Similar thing is going on here. Yes. Yeah. So, that is why we are going through this route. Okay. So, this particular thing, what is happening here is now you have impulses showing up for u of t, you have this, whereas if you look at the bilateral, so this is the CTFT, whereas u of t, if you consider just the Laplace, so this is 1 over S, and this of course is real S strictly greater than 0. If you replace S by j omega, you will only get this term, you will be missing this impulse. So, for more discussion on this, you can look up Professor V.G.K. Murthy's lecture, Networks and Systems on NPTEL. So, he has one specific lecture devoted to this, where he takes a Laplace transform and then shows why for certain functions you cannot replace s by j omega, and then for these cases impulses will show up in the transform domain, and it will be very beneficial to look at that particular lecture. So, Networks and Systems by Professor V.G.K. Murthy, NPTEL. Now, since we have the inverse DTFT definition, this is h of e to the j omega and this is 1. So, h of e to the j omega is 1 for mod omega less than omega c and 0 otherwise. By otherwise I mean in the interval minus pi to pi, because this after all is periodic with period 2 pi. So, this is your ideal low pass filter, and it is very easy to obtain the impulse response. So, this is 1 over 2 pi minus pi to pi h of e to the j omega times e to the j omega n d omega, and in this particular case this simplifies to minus omega c to plus omega c e to the j omega n d omega, and this is immediately seen to be sine omega c n by pi n. And if you recall, we had used this sequence when we were demonstrating the use of one of the properties, that is, if you sum up the sequence over all n, it is exactly the same as the value of the transform evaluated at omega equal to 0, right. And if you look at this case, the value of the transform at omega equal to 0 is 1. Therefore, this impulse response summed up over all n gives you 1. In that context, we had seen this particular example, and we had also used this example in Parseval's relationship. So, this transform pair was just mentioned without proof, and now we are seeing the proof here. Therefore, sine omega c n by pi n is your ideal low pass filter with cutoff omega c. By the way, this impulse response, if you, the sum up over all n of this is 1, which is the illustration of the property that if you sum up over time domain sequence, you evaluate the Fourier transform at omega equal to 0. So, that is clear. But what about this being the impulse response? What about sum over all n of magnitude of h of n? Very good. Do others see this as well? So, for this particular case where h of n is sine omega c n by pi n, this value is okay, this is a basic result that you should have known. So, this is what? What's the value? He said the right answer, but oh, so you arrived at the answer by thinking it was constant times 1 over n? Then I am not sure the proof that you are outlining is fully correct. You need to look this up. Anyway, so this is, in case you have not seen this, this is not absolutely summable. So, this is not absolutely summable. Therefore, the ideal low pass filter is not a bibo stable system, all right. And this is no different from what is happening in the continuous time case. The ideal low pass filter in the continuous time case, its impulse response was just replace little omega c by cap omega c, and then instead of the highest frequency being pi, the highest frequency will be infinity. Therefore, if you had the ideal low pass filter in the continuous time case, its impulse response was what? It would be sin omega ct by pi t, all right. The ideal low pass filter's impulse response in the continuous time case is sin omega ct by pi t, and that impulse response is not absolutely integrable. Therefore, even in the continuous time case, the ideal LPF is not a bibo stable system. So, this is the counterpart of that. So, just I am making this observation in this context, that is all. And once you have the impulse response of the ideal low pass filter, its counterpart, the ideal high pass filter with the same cutoff, so this impulse response is what? Very good. You can think of this ideal high pass filter as 1 minus the frequency response of the low pass filter. Therefore, if the frequency response is 1 minus the frequency response of the low pass filter, the corresponding impulse response will be delta of n minus sin omega cn by pi n, that is all. So, this is, let me use the suffix h suffix cap hp. So, this is to indicate it is high pass, and if I wanted to be consistent, I should have written this as h LP of e to the j omega. And as an exercise, I want you to find the impulse response of an ideal differentiator. In the continuous time case, the ideal differentiator, the frequency response is the frequency response of an ideal differentiator in the continuous time case is j omega, right. So, there it is j omega over all of omega. All of omega means omega going from minus infinity to plus infinity. Here in the discrete time case, the frequency response of the ideal differentiator is still h of omega equals j omega, except now it is restricted to the range minus pi to pi. Therefore, so this is your ideal differentiator's frequency response. So, this is h of e to the j omega being j omega between minus pi and pi. So, I want you to find h of n. So, it is a very simple integral. You have to use udv formula. Okay. Okay. So, for example, if you pass cos omega naught n to a differentiator, what do you expect? So, it is in that sense. The other way of doing this, which will require some thinking, is you can use the derivative property. What I want you to do is get h of n using the straightforward approach. It will be, after all, 1 over 2 pi minus pi to pi of the integral will be j omega times e to the j omega n, because h of e to the j omega is j omega, and that you can very easily derive using the UDV rule. So, you will know what the final answer is as far as the impulse response goes. See if you are able to get the same answer using the differentiation property. It will require some thinking.